Previously, we talked about alkyl halides and their nomenclature in chapter 4. In this chapter, we are going to talk about two general types of reactions that alkyl halides can undergo. We call them substitution and elimination reactions. So substitution reaction is pretty easy to follow, as we are basically substituting one group with another. However, the challenge gets started as soon as we talk about elimination reactions, because you then need to decide which reaction is preferred based on the starting material and the reaction conditions that you are working with. As I mentioned, there are two general types of reactions that we are going to study in this chapter: substitution and elimination reactions, and for both of them, the reaction will take place on a molecule that we call substrate. Substrate is a molecule that can react during the course of the reaction, and specifically for substitution and elimination reactions, we are looking for a molecule that has a leaving group attached to it, such as halogens, water, and tosylate. We are going to talk about that later. Also, you will hear me talking about reagents. So reagents are compounds or substances that are added to the reaction to cause the chemical reaction happen. Talking about the substrate, one of the best substrate in substitution and elimination reactions are alkyl halides. There are a couple of reasons that make them a very good substrate for these kind of reactions. First, halogens in the alkyl halide withdraw the electron density from the adjacent carbon, rendering that carbon to be electrophilic, which is very important during the substitution reaction. And also, halogens can act as a good leaving group. And substitution and elimination reaction can happen only if we have a leaving group in the molecules. Therefore, alkyl halides are very good substrate for us. We know the halogens, so they are fluorine, chlorine, bromine, and iodine. And among them, fluorine cannot act as a good leaving group because it is the most electronegative atom, and it's too reactive to work with in the lab, so we just don't use it. Majority of the time, you'll see alkyl chloride, alkyl bromide, and alkyl iodide as a substrate for substitution and elimination reactions. A general rule is that a good leaving group is a conjugate base of a strong acid with pKa less than 0, because they can stabilize the negative charge after leaving the molecule. So the pKa prefers to be less than 0. And here is the table of all leaving groups. So the best leaving groups that we can deal with are water, tosylate. This is the structure of tosylate. We are going to talk about that later. Chlorine, bromine, and iodide. And if you compare their acids, so all of them, they have the pKa less than 0, which makes their conjugate base a good leaving group for our purposes. In alkyl halides, we have different positions to consider: alpha and beta position. The alpha position, or the alpha carbon, is the carbon that is directly connected to the leaving group. So imagine if bromine is our leaving group, this is going to be our alpha carbon. And substitution reaction is occurring at the alpha position. We can also have beta position in the alkyl halide, so the carbon right next to the alpha position is a beta position, and specifically in this example we can have two beta positions. Elimination can happen at beta positions, and a lot of the times we need to choose which beta position gives us the more stable product, so that one can react. Also, alkyl halides can be classified as primary, secondary, and tertiary. So if we have one alkyl groups connected to the alpha carbon, we call that primary alkyl halide. If we have two alkyl groups connected to the alpha carbon, we have secondary alkyl halides. And if we have three alkyl groups connected to the alpha carbon, we call that tertiary alkyl halides. A general comparison between the substitution and elimination reaction is shown here. So in substitution reaction, we are basically substituting a leaving group with another group which we call nucleophile. So a nucleophile attacks the alpha carbon, leaving group leaves to form the product. So basically in the product, the leaving group is substituted with the nucleophile. However, in elimination reaction, a base attacks the proton in the beta position, forms a double bond, and leaving group leaves to form the alkene. So the product for the elimination reaction is an alkene. These two reactions oftentimes compete with one another. However, there are some specific features in both of them that we are going to study in this chapter, which can help us to figure out which is happening. Let's look at the first type of substitution reactions, which we call that SN2 reaction. So in SN2 reaction, nucleophile attacks the electrophile and leaving group leaves to form the product. So we are basically substituting the leaving group with the nucleophile. SN2 involves nucleophilic attack and loss of leaving group. Both are happening at the same time and in one step. So we say the SN2 mechanism is a concerted mechanism because both of these processes are happening at the same time. So let's look at the example for SN2 reaction here. So this is the example of alkyl halide. This carbon is our electrophile because it is connected to the electronegative leaving group. So this is our electrophile. And sulfur is our nucleophile because it has lone pair of electrons to share basically. Therefore, the nucleophile attacks the electrophile, and at the same time leaving group leaves to form the product. In SN2 reaction, the rate of the reaction is also dependent on the concentration of both alkyl halides and the nucleophile. So we can write the rate equals rate constant, concentration of the substrate. So we can say the substrate here is alkyl halide and the concentration of nucleophile. So if we double the concentration of the alkyl halide, the rate will be doubled. And if we double the concentration of nucleophile, the rate will also be doubled. So as I mentioned, the mechanism here is concerted and it involves both substrate and the nucleophile. So the reaction is bimolecular. Now if you look at the name of SN2, so S means substitution, N is nucleophilic, and 2 is written there because it's bimolecular. We can also draw an energy diagram for the one-step process such as SN2 reaction. So we need to plot the potential energy versus reaction coordinates. And this is the energy diagram for the SN2 reaction. So we have substrate and nucleophile as our starting materials. We have product and leaving group right there, and right here we have our transition state. This is the sign for transition state. So it's a one-step process. In SN2 reaction, if our alpha carbon is a chirality center, we will see inversion of configuration, meaning that if the alkyl halide shows S configuration, the product will show R configuration and vice versa. So why do we see inversion of configuration? Here is an example that is shown inversion of configuration. Let's draw the mechanism for this reaction to understand this concept better. So this is the substrate, and this is the nucleophile. So nucleophile attacks the electrophilic center and leaving group leaves to form this transition state. Okay, and then after passing through this transition state and loss of leaving group, this product is forming. So this is a one-step process. As our nucleophile is coming in to attack the electrophilic center, the leaving group is leaving. So the leaving group hasn't left as the other group is attacking. So you can imagine where is it going to be more space as the nucleophile attacks. Is that the front side or the back side of the substrate? Clearly the back side, because the leaving group is blocking the front side. So nucleophile can only approach from the back side. And upon the backside attack, we are going to see this transition state. So the dotted line between sulfur and carbon shows that the bond is forming between the nucleophile and the electrophilic carbon. The dotted line between bromine and carbon shows that the bond is breaking between the leaving group and the electrophilic carbon. Also in the transition state, you'll see the nucleophile is coming from the opposite direction of where the leaving group, the bromine, is leaving. So when nucleophile is coming in and attacking the electrophilic center, it shifts all the groups that are attached to the electrophilic carbon to the opposite direction, and that causes inversion of configuration. So to check we have inverted stereochemistry, we can assign R and S configuration for both substrate and the products. So let's do that together. In the substrate, bromine is number 1, ethyl is 2, methyl 3, and hydrogen is 4. So let's count. We are counting 1, 2, 3. It is clockwise and the lowest priority is pointing towards me. So the configuration is S. Now in the product, sulfur is 1, ethyl is 2, methyl and hydrogen. So again, let's count. It is 1, 2, 3. Rotation is counterclockwise. The lowest priority pointing towards me. So it is going to be R. So we'll see the inversion of configuration S to R in this example. Also, we call SN2 reaction a stereospecific reaction because the configuration of product is dependent on the configuration of a starting material. So the stereochemistry of the substrate, the starting material, matters to figure out what the stereochemistry of the product would be. So therefore, SN2 reaction is a stereospecific. Let's look at another reaction for SN2 mechanism. So we can have this substrate that react with this nucleophile. So the nucleophile will attack the electrophilic carbon and the leaving group leaves. So since we are forming the chiral center in the product, we need to show inversion of configuration as well. So we started with the substrate where the bromine is in wedge. Now in the product, the nucleophile, the sulfur nucleophile, will be in the dash. So we have inversion of configuration here. In this practice problem, we need to define an electrophile, a nucleophile, and the mechanism. And we need to decide whether the product would have a stereochemistry or not. So let me label these two structures. So in structure A, we can see an alkyl halide. Our leaving group is iodine here, which also makes this carbon an electrophilic carbon. So compound A can act as an electrophile. And in compound B, we have oxygen, which is negatively charged, so it can act as nucleophile. Now that we define electrophile and nucleophile, oxygen can attack this carbon and leaving group leaves. So the product would be this structure, and this is going to be the bond that formed between the nucleophile and the electrophilic carbon. Now, do we need to show stereochemistry and inversion? No, because this carbon is not a chirality center, so we don't need to show inversion of stereochemistry here. Another question that can be asked here is why not iodine acts as nucleophile and attack the carbon of carbonyl? So we know that this carbon is an electrophilic carbon, so why not iodine attacks it and forms the product? To show that this reaction cannot happen, let's look at this example. So imagine this is our alkyl halide and we have an electrophilic center such as carbocation. Now if iodine acts as a nucleophile and attack the carbocation, we are going to form this product. Okay, and iodine will get a positive charge on it. Now this molecule, this species, is very reactive and very unstable. So it is not favored. Formation of it's not favored at all. Therefore, whenever you have alkyl halide, it doesn't matter you have iodine, bromine, or chlorine, never halogen in the alkyl halide attacks the electrophile. So this is completely unfavored, and never think about it while drawing mechanism for reactions. What's the effect of the structure of substrate in SN2 reaction? Rate of SN2 reaction is sensitive to the nature of substrate. Because SN2 is a second order reaction, you can look at the rate law and see that. So the rate depends on substrate. The less sterically hindered alkyl halide react more rapidly under SN2 condition, meaning that the methyl halide is the most reactive alkyl halide under SN2 condition. The moment that you replace one of these hydrogens with the alkyl group, or basically you are adding alkyl group to the alpha carbon, the rate of the reaction decreases drastically in a way that the tertiary alkyl halide is too hindered to react via SN2 mechanism. So why is that? If you look at this structure. So this is the structure of tertiary alkyl halide. Now, if the reaction wanna happen via SN2 fashion, the nucleophile should attack the alkyl halide, the electrophilic center, from the backside. Now, if the nucleophile wanna reach to alpha carbon, there are a lot of electron density on alpha carbon. So the tertiary carbon is sterically hindered. So it's almost impossible for hydroxide to attack the alpha carbon from the backside. As soon as we replace one of these carbons with hydrogen, basically we are providing more space for the nucleophile to attack to the alpha carbon, and the reaction happens faster. Therefore, the steric hindrance on alpha carbon is not favored in SN2 reaction. So the less steric hindered alkyl halide is always favored. Basically, methyl and primary and sometimes secondary can be very good substrate for SN2 reaction. So this was an example of a steric hindrance at alpha position. Now, a steric hindrance at beta position can also decrease the rate of the reaction. So if you look at this example, this is alpha carbon, this is beta. So this alkyl halide is primary, so we expect to do SN2 reaction. However, it has a very large group, like tertiary butyl group, at the beta position, which can hinder the backside attack by the nucleophile. So this substrate is essentially unreactive towards SN2 reaction. So this is primary, but it is essentially unreactive in SN2 reaction. So we can also have some example of large group that can provide a steric hindrance. So one of them is tertiary butyl, that chicken finger we talked about. So this is tertiary butyl. And the other group can be phenyl. So these are very large group that can make a steric hindrance at beta position. Substitution reaction can also happen through SN1 mechanism. So here again we are substituting a leaving group with the nucleophile, but in a stepwise manner. So in the first step, what's happening? We have loss of leaving group. So leaving group takes the bonding electrons and leave the molecule to form the carbocation. Then in the next step, a nucleophile will attack the carbocation to form the product. So all of these processes will happen in SN2 reaction as well, but here it's happening in a stepwise process. Now, since the intermediate that we are forming is a carbocation, we need to consider the chance of rearrangement in the carbocation. So if the carbocation that we form can do rearrangement to become more stable, it will definitely do it. Now let's talk about stereochemistry in SN1 mechanism. So if the alpha carbon that we are forming in the product is a chirality center, we are going to form a racemic mixture. And if you remember, a racemic mixture was the mixture of both enantiomers. So let's look at this example. So imagine that we have this substrate. So through SN1 mechanism, what should happen first is that the leaving group leaves the molecule. So the leaving group leaves the molecule, and we are going to form a carbocation. So since we are forming a carbocation, if that carbocation can do rearrangement to become more stable, it will definitely do it. However, here we cannot form a more stable carbocation. So in the next step, A nucleophile will attack the carbocation to form the product. Now this carbon in the product is a chirality center. So it is connected to 4 different groups. Therefore, we are going to get a mixture of both enantiomers. So we are going to get the mixture of R and S. So this is racemic mixture, which is the 50-50% mixture of enantiomers. Now, why do we get racemic mixture? Because if you remember, carbocation, the hybridization for carbocation was sp2, meaning that carbocation is planar. So the nucleophile has equal chance to attack the carbocation from top and from the bottom and form both of these products. But when we are drawing the arrow, we just show one arrow that the nucleophile attacks the carbocation. So you don't need to show both arrows from the top and from the bottom. But what you need to know is that we are forming a mixture of enantiomers, which is a racemic mixture in SN1 mechanism, if the alpha carbon becomes a chirality center. In SN1 reaction, the rate of the reaction is only dependent on the concentration of the substrate. So if you draw the energy diagram for SN1 reaction, we are going to see a two-step process. So most of the time SN1 reaction is a two-step process unless the carbocation does rearrangement. So we are going to have three-step process. Now the starting material would be our substrate with the leaving group attached to it. Then we are going to pass through the first transition state, which involves loss of leaving group, to form the carbocation. So carbocation is our intermediate, and then the nucleophile will attack the carbocation to form racemic mixture. So, and racemic mixture is a mixture of enantiomers, so they both have same energy. Now if you look at the activation energy for these two steps, the activation energy for the first step is much higher than the second one. So the first step has higher energy transition state, meaning that this step is slower than the second one. And in chemistry, the slower step is always the rate determining step. So if we want to define the rate law for the reaction, we need to look at this step only. And in this step, we only have the substrate that loses the leaving group. Therefore, the rate is only dependent on the concentration of the substrate. So the rate determining step involves only one entity. Therefore, we call that it's the unimolecular reaction. Now, if you look at the name of SN1 reaction, so it's a substitution, nucleophilic, and unimolecular reaction. As I talked before, in SN1 reaction, we are forming a racemic mixture, meaning that the stereochemistry in SN1 reaction involves retention of configuration and inversion of configuration. So what does that mean? So look at this example. This is a tertiary alkyl halide, and through SN1 reaction, the first step is loss of leaving group. So leaving group leaves, to form the carbocation. Okay. So we have a tertiary alkyl halide and the leaving group leaves to form a carbocation. We know that the carbocation has an empty p orbital on it. Okay. And carbocation has the hybridization of sp2, so carbocation is planar, meaning that if you add a nucleophile such as chlorine, the nucleophile can attack the carbocation from the front and from the back completely equally to form both products with retention of configuration and inversion of configuration. So we are going to form two products. If the nucleophile attacks from the front side, we are going to have retention of configuration. Okay. And if the nucleophile attacks from the back side, we are going to have inversion of configuration. So both of these products will form. One of them shows retention of configuration and the other one shows inversion. So to show the nucleophilic attack here, you don't need to show it for both sides. One side would be enough, but we know that we are going to make two products, one with retention of configuration and the other one with inversion of configuration. Now to check that, let's identify the configuration on the starting material and the products. So bromine is 1, propyl is 2, 3, and 4. So this is going to be 1, 2, 3. If you count 1, 2, 3, okay, this is going to be S because the lowest priority is in the back. And in this one, we also form the S configuration. So this is 1, 2, 3. It is S, the lowest priority is in the back. And in the next structure, this is going to be R. This is 1, 2, 3, and 4. So if you count 1, 2, 3, this is R configuration. So basically these two structures are enantiomers to one another. And this is the racemic mixture that we form during the SN1 reaction. Now, how does the structure of substrate can influence the rate of the reaction in SN1 reaction? So the most reactive alkyl halide would be the tertiary alkyl halide. And the least reactive one, or I can say the unreactive one, is methyl halide, which is completely opposite of SN2 reaction. So why this pattern arises? So think about the mechanism. Why SN1 prefers a tertiary substrate over the primary? In SN1 mechanism, we are forming a carbocation. So if you look at here, this is the carbocation that can be formed. And we talked about it in chapter 6. A tertiary carbocation is more stable due to hyperconjugation processes. A hyperconjugation happens when the carbons, the CH bonds, next to the positively charged carbon can donate electrons to the p orbital, which makes the carbocation more stable. Now, the challenge with SN1 reaction is that you should always consider the rearrangement possibility, because if you are forming a carbocation and that carbocation can do rearrangement to become more stable, it will definitely do it. So always consider possibility of rearrangement in SN1 reaction. Now let's look at this practice problem. So this is a SN1 mechanism, and we are supposed to draw that mechanism for this reaction. So let's draw the mechanism here. The substrate that we have is an alkyl halide. Okay. Since this reaction is happening through SN1 mechanism, the first step is loss of leaving group. So chlorine leaves the molecule. To form this carbocation. Now, by looking at this carbocation, can this carbocation do rearrangement and become more stable? Yes. So we have hydrogen here. So this carbocation can do H shift to form more stable carbocation. Okay, so this one was secondary, and this structure is a tertiary carbocation. Now in the next step, water will act as a nucleophile. So we have water on arrow. So water will act as a nucleophile and attacks the carbocation to form this product. Now, oxygen with 3 bond is positively charged. So if you compare this structure and the structure of alcohol, which is our product, how can we convert this structure to the desired product? So obviously oxygen should lose one of its proton. So what will happen here is that another molecule of water will act as a base and removes one of the proton in this structure to form the desired product, and the hydronium ion. Now in the product, do I need to show stereochemistry here? Do I need to show that I get a racemic mixture? No, because this carbon is not a chiral carbon. This part of the molecule is exact similar as the other part. Therefore, I don't need to show the stereochemistry here. So I'm going to get only one product in this reaction. Now, another question that can be asked is, why doesn't chlorine come here and take the proton from this intermediate? The answer for this question is in pKa values, because if chlorine takes one of these protons, it will be converted to the HCl. Now, if you compare HCl with this intermediate, HCl is very, very strong acid. Therefore, the equilibrium does not form that. So if you remember, equilibrium always prefers formation of a weaker acid, and this acid is weaker than this intermediate. So therefore, water can act as a good base to form this product.